Laboratory 4 involves utilizing this software package known as Pymol. So Pymol is a very unique and very powerful tool for visualizing three-dimensional structures of proteins. The important caveat to that is that the protein structures have actually been solved. They've been solved by NMR or by X-ray crystallography. So we know in three-dimensional space where every atom is located and in X, Y, and Z coordinates. So what Pymol does is it actually reads what are known as PDB files. So in order to do that, first thing is we have to install Pymol. So this is a link to install the educational version of Pymol, which is free. And then you have to look at some protein data bank, somewhere where the coordinates of all these solved protein structures are available. And one place that they are found is known as the protein data bank. So you can just Google protein data bank, or you can just simply, so here's the protein data bank, and every protein that's been deposited into the PDB has a PDB ID number. So you can search for a particular protein that you're interested in, or if you already know that solved protein structures PDB ID, identification number, you can put it right in. So we need to first download the coordinates. Once again, the coordinates are every atom of that protein molecule. Its X, Y, and Z coordinates are known. So we can copy and paste that into the PDB and download the coordinates. So I'll do just that. I'll type 1BPN, or I can copy and paste this. And here we have the structure of the binding site for inositol phosphates in a pH domain. So let's download the PDB file associated with this structure. So we'll go to Download Files, and then under Download Files, we'll click on PDB Format. And I'll just download it straight to my desktop here. So on my version, since I already have Pymol installed, I can just click on the PDB file and it should open up. And there it is. Let me minimize my internet browser here. And I'll minimize the Word document. So now I just have Pymol running on my screen. And you notice that Pymol as a software has two windows. A window where you can actually do coding if you're interested in coding. So Pymol does have a syntax associated with it, but you can also do mouse control features using some of these windows here. That's what the first window contains. The second window is the actual viewer. Now I have the structure, just a few words on the mouse. You can click your left mouse and you can rotate the molecule. So I'm holding on to my left key on the mouse. That's a rotation. The right key, the rightmost button on my mouse is zooming. So I can zoom up or down using the rightmost key. A middle mouse button is a translational. Okay, so here we rotate using the left mouse button along the X or Y axis. The middle mouse button does translation, either an up or down translation or a left to right translation. And the right hand mouse button does a zooming. It moves along the Z axis. The Z axis is the axis pointing towards you and away from you. So I'm going along the Z axis here. So I can zoom in on a particular part of this molecule. The name of the molecule, once again, is a binding site for inositol phosphates in a pH domain. So we're actually looking at a domain of a larger protein. Remember, a domain is an independently folded unit. And if we go to display here, we can display under display sequence, and we have the primary amino acid sequence. We also have a signal molecule known as I3P. If I click on that, you notice that a select button appears, and also notice that I've highlighted I3P, or inositol triphosphate. If I mess up which is very common in a complicated software like Pymol, I can just click on the black and just reset myself, and I can remove the selection here. So there are ways to remove your selection. A stands for action, S stands for show, H stands for hide, L stands for label, and C stands for color. So the action that I want to perform now is just delete the selection. Every now and then you're going to need to just reset or recalibrate yourself. Just click on the black. Now what are these O's here? The identity of these O's are nothing more than water. So these are water molecules that actually have come along and have crystallized with the crystal structure of the actual protein. So water, you notice here if I click right on the viewer, it will actually tell me in my top window the molecule that I have labeled. So if I look here, I click on that, I have actually selected water 184, more specifically the oxygen atom. So let's just click on black in the background and just get away from this all. Every time I click on any molecule, it's going to appear as a selection. So I can just get rid of that selection here. But what I'd like to do now is this 1BTN is the PDB ID number. And I can do many things. One thing is, if I don't know what BTN is, I could just change the name of the subject, or excuse me, I can change the name of the object. So if we go to rename object, I'll change 1BTN to the actual name of this molecule, and that is spectrin. Spectrin has 2 pH domains. So this is just a little bit more clarity for me. So I can continue to play along with this. One thing I can do if I want to pretty up the structure or make the structure look something nice for a publication, or if I want to look into see which amino acids are close to one another, I could actually change some of the parameters or the visualization. One thing I normally like to do, this is just me, you may be a little different, I like to hide the waters. So H, as we said before, stands for hide. So I'll hide waters, and my waters are no longer there. As we remember, a protein consists of the peptide backbone and side chains. So I see a lot of my side chains here. I'm not so sure where my protein peptide backbone begins, nor where the N terminus or C terminus is. What I can do is I can show, the S stands for show, I can show as a cartoon. And now I have labeled here the secondary structure components. I have some helical structures, I have some beta structures, there's another bent beta, and then I have an alpha helix here. And what do you think these represent here? Okay, so these are the side chains that are shown in a stick format. So I could remove those, I can keep those, I can select the ones I would like. For now, I'll just show this as, for now, what I will do is I will just hide the side chains. And now I've hid the side chains. And what do I have still remaining as lines or sticks? You should realize what you have remaining as the lines or stick representation is the peptide backbone. So we'll hide the main chain. We've already hid the side chain. And now we have the plextrin homology domain of this protein known as spectrin. You notice here that it's being bound to another molecule. So if I click on this molecule, it's being bound to IP3. IP3 stands for inositol triphosphate. The minute that I select that IP3, it occurs or it appears as a selection. So I could relabel that selection as rename selection as IP3, because that is what I've selected. It's a small molecule that has co-crystallized with IP3 is a signaling molecule. So if you've taken a signal transduction course or an immunology course, you'll be familiar with IP3. And here is the signal molecule interacting, looks to be interacting with this random coil region of the plextrin homology domain. Let's go back to our main protein spectrum. If I click on spectrum, I get that back. And let's just color this based on secondary structure. So if I go to C, I'm coloring the actual protein C. And let's color by secondary structure. I'll keep my helix red, sheet yellow, and random coil green, though you can color it any which way you please. And I have a very nice version of spectrum. Okay, it's a very beautiful ordered structure with helix, beta, and a random coil interacting with this small molecule which co-crystallized with that IP3. I could take that IP3, let's delete the selection. I can take this IP3 and I can show as, let's show it as sticks. And let's color the sticks by element. And you can pick whatever element you want to color it by. And here is my IP3 molecule interacting with spectrum. So let me zoom in here with my third mouse key. Take my middle mouse key and let's just look to see some distances between an amino acid here and perhaps one of the atoms on the IP3 molecule. So I will go to under the wizard key, I will click on measurement. And it asks me to pick the first atom. So let's just pick this atom here. Or maybe I'll just pick this atom that's closest. And I have picked an oxygen, oxygen 11, on this IP3 molecule. And now let's click on the second atom. Let's click on an atom that is maybe in this random coil region. And I've picked on serine, the alpha carbon of serine at position 22, and I've noticed that we have a distance of about 5 angstrom between this oxygen of IP3, oxygen 11, and this serine, this alpha serine carbon, the alpha carbon of serine that's associated with this random coil region. So that's measurement 1, and I can continue to do this until really the cows come home. Let's determine the distance here between along the axis of this red alpha helix. So I'll pick on that one. I picked on aspartic acid 93, it's alpha carbon, and then this one here, and that's 6.2 angstroms between aspartic acid 93 and asparagine 97. Notice it's about 4 residues away as we go down the alpha helix. So I can continually do this. I'll just click done for now. And we're able to get interatomic distances across the helix. And then from this small molecule that co-crystallized with the protein with regions of the actual protein. If that amino acid is important, let's say this serine is important, I'll click on it. This appears as my selection. I will rename the selection as serine 22. Hit enter. And let's just show the serine 22 as sticks. And it's green. Maybe I don't like green. Let's just label it the atoms in a different color. And I have the alpha carbon of serine. Let me zoom in using my third mouse key and then my middle mouse key. Here's that serine, 4 angstroms away from that oxygen. I can also use the wizard to label it. And let's label this atom here as IP3 107. That's actually an oxygen atom. And then let's label this as serine. So that's serine 22. If I want to look at angles, such as dihedral angles, we can also check out dihedral angles as well. So a dihedral angle is going to be defined by 4 atoms. So if we go under wizard, we have measurement. And instead of angles, we already looked at distances. Now let's look at dihedrals. So let's look at dihedral angles across perhaps this alpha helix across the main vertical axis of this alpha helix. So a dihedral angle is determined by 4 atoms. Let's just show on our spectrum molecule here. Let's just show on our spectrum molecule here. Let's just show the main chain. We'll just show it as lines. So here's our main chain with all the peptide bonds that's running along the alpha helix. Let's determine the dihedral angle. So let's zoom in across this main alpha helix. So let's look at dihedral angles across the peptide backbone. So for that, let's go to this beta sheet region here, and we're on dihedral. So I'll click on my first atom here, and that is going to be the oxygen of glutamic acid 10. Let's click on our second atom here. I'll click on the alpha carbon of glutamic acid 10. Let's pick here the third atom. That is the oxygen atom of the peptide bond to histidine 9. And then finally, across this beta chain or beta sheet, I'll click on this third atom. And here we have a dihedral angle of 159.8 degrees. So that is an accessible dihedral angle for a beta strand. So let's delete that measurement here that we just created. We can also look at regular angles. So if we go under the wizard and measurement, instead of dihedrals, we'll look at angles. So let's focus here on maybe this random coil region. We'll select our first atom. Let's select it across the peptide backbone. So our first atom is going to be the oxygen of histidine. And what is the angle between that oxygen of histidine of the peptide backbone and this alpha carbon of asparagine 15? And then we need 3 points to define an angle. Let's do this here, the nitrogen of lysine, and that 3 atoms are held together by an angle of 69.4 degrees. We can play around with the syntax. In the command line, we can type in set label size 16, set label color black, and background color white. So Pymol has its own code, so we can play around with the code a little bit here, though many people don't like learning code. You notice you can see a shadowing effect in Pymol. You can also do all of that without the syntax and put the background as, well, let's just remove the opaqueness of the background and we can make it gray or light gray. All right. So we've finished our first Pymol session. We can save the session. I'll just save it in my desktop and we'll save it as Spectrum. That is our session. We can always go back into it. We can also save the image as a PNG format. Let's save the molecule also. So I'll save the image as a PNG molecule. I'll save it as my desktop here, spectrum.png, a file that we can use as a picture. So we already have the session available, so we can exit out of here, quit, and we can go back and play around with that. But we also save the file as a PNG file, so we can open it in PowerPoint or in Word. So I'll open up PowerPoint, and under PowerPoint, we'll hit Insert Pictures, and in my desktop, I should be able to find my spectrum, and there you go. We got our distances across the length of 2 amino acids across the alpha helix, distances from this co-crystallized small molecule with an amino acid serine that's close by to it. We figured out some dihedral angles as well as angles across the peptide bond. One of the nice things about Pymol is that it could align protein structures. Right now it's only capable of aligning 2 crystal structures or NMR structures. The PDB ID number for human lysozyme. So let's go back to the PDB and put that number in, the ID number. We'll download the PDB format and it's downloaded. Let me rename that as human lysozyme. So maybe human LYZ. And let's do the exact same thing we've done before. Let us click on the black here, get rid of this selection. let us hide the waters. This is just me. This is how I like to portray my structures. And just for convenience sake, I'll hide the main chain and the side chain, so we only have pure secondary structures that we're looking at. The chicken version of lysozyme has a PDB number of 4IAT. Before we do that, let's look at our directions here, and let's check and look at some important residues of the human version of lysozyme. Let's check out the aspartic acid residue and the glutamic acid residue. Those are the ones that are involved in lysozyme's active site, aspartic acid and glutamic acid. If you remember, it was aspartic acid 53, so I will rename this selection as ASP 53. Hit enter, and we'll show this as sticks. And there you see your ASP 53. Let's just color that a nice different color here. Okay, so that's your ASP 53. That's part of the protein's catalytic site. The second one is actually glutamic acid 35, so 31, 32, 33, 34, 35. There's that. And I will label that selection. And let's label that as show as sticks. And we'll color that the same way. And here is aspartic glutamic acid and aspartic acid. We can also label our residues. So here I have the 2 amino acid sites labeled that are implicated in active site catalysis. Let's look at the chicken form of lysozyme, and that one has an PDB number of 4IAT. So here's the chicken version of the lysozyme, PDB format, 4IAT. And let's open that up in the same window. So under File, Open, and under my downloads directory is 4IAT. And here is 4IAT. Now don't worry, your human lysozyme and the 2 active site residues that you found are still there. So what you can do is right-click and hit Center. So you can see it's still there in the background. Let's do everything that we've done with the human one to the chicken one. So first let's relabel this. So we'll rename this object as hen lysozyme, hen underscore FYZ, and we'll hide the waters, and we'll show as a cartoon, and I like to color my secondary structure. And let's just hide the main chain and the side chain to make our things a little bit nice. Okay. Let's also look and select our catalytic residues. Here is the aspartic acid, and here is the glutamic acid, and here is the aspartic acid. So here is, rename that, hen asp 35 and B51. Hit enter. Let's show these as sticks. We'll color them a certain way, and let's label these atoms. So if you want to label it, go under Wizard, Label, and let me zoom in here now. Just select the atoms. That's one, and then here is the other. Click Done. And now I have in both my windows the human and chicken lysozyme. I'm ready to line them up to see how close the human and chicken version of the lysozyme are. So in order to do that, let's follow our prompts here. We will type in align human Now, I'm going to align them to whatever object you name them by. So I did not name my object human lysozyme, and I did not name my object HEW lysozyme. So I'm going to use the function align. And I'm going to align human underscore LYZ, because that's how I named my object, comma, hen underscore LYZ, because that's how I renamed my object. And the alignment was successful. It went very fast. We had an RMS deviation of 0.519. You can see that the RMS deviation is taking all the atoms, their distances, summing them up, and dividing it by the number of atoms. So your root mean square deviation, you want to minimize that number. And let's go back to this. If you look very carefully between the hen and chicken lysozyme, I want to bring particular attention to the conserved amino acid residues of aspartic acid and glutamic acid. If I zoom in, you notice how they line up, okay? Almost perfectly. I have a little bit of a distance gap here amongst the side chain. In fact, I can get the distance of that. Okay, the distance between this oxygen atom and this oxygen atom is, well, there's a 1.5 angstrom deviation. That's not too bad. You can see here that this amino acid, your glutamic acid, lines up really well. I'm sorry, your glutamic acid lines up almost perfectly. Let's take a look at the distances between these two oxygen atoms in the alignment. .4 angstroms. So we see we have very good alignment across the two catalytic residues involved or implicated in the active site. I'm done with this, so I can click done. Where is the deviation? Well, most of the deviation is in the random coil, okay? But where catalysis occurs, there is a lot of alignment. So a chicken lysozyme and a human lysozyme look remarkably similar, and they're remarkably similar at the catalytic fold, and even the amino acids that are involved in catalysis line up almost perfectly. The whole structure lines up really well if you look at the helices, the red helices, and the beta. And as we said before, a little bit of deviation at the coil region. The coil region probably doesn't have much function. It's probably there just to keep the structure proper so that catalysis can occur. Alignment that you'll have to do, and that is between 3PU7 and 2VOA. So let's take a look at that here. 3PO7, you're going to want to line up 3PU7, which is superoxide dismutase from tomato, and you'll do the exact same thing with 2VOA, human superoxide dismutase. So the alignment between 2,0A and the alignment with 3PU7, you're going to line up tomato superoxide dismutase with human superoxide dismutase, and you'll see what you'll get. Turn that in as a PowerPoint slide along with your alignment of lysozyme, along with a third PowerPoint slide that has your spectrin molecule, and turn that in for some points as credit. Let's save this alignment as save PNG. Save it as alignment. And then our second PowerPoint, we will insert picture. We'll insert our alignment. Make sure you put in your RMSDA value, alignment of. So do the same with your tomato and your human superoxide dismutase. Save the file and turn that in along with the other homework from your previous week. Thank you. I thought I would take this moment to show you the anatomy of a PDB file. So if you go and open up Microsoft Word, and instead of using Pymol to open up your PDB file, you actually open up your PDB file in Word. So we will go and open, and here's your PDB file that I have put in my downloads folder. And let's open up this file in Word and see what you get. Now remember, you opened that PDB file in Pymol and it rendered to you a three-dimensional structure. But this is actually the anatomy of a PDB file. It is actually a text file, and you can see here information that was very familiar to the NCBI. In fact, the NCBI and the Protein Data Bank are often linked. And you have the title, compound, you have accession numbers, organisms from which the structure came of. So I actually opened up the PDB file 4IAT, which represented the crystal structure for hen egg white lysozyme. And you can continue to scroll down. This is a crystal structure, so all these terms you see here, such as R value and bin resolution, they have to do with the statistics in determining the crystal structure. So this is a topic way beyond this course, but when you do a crystal structure, you're actually fitting electron density that is diffracted from the crystal. In this case, you've grown crystals of lysozyme. And you can continue to go down. This is a very large document, and it's about 50 pages if you notice. Here you can see regions that are designated as a helix. But what does Pymol actually read? Okay, remember a PDB file is the solved structure of that protein via crystallography or NMR, and it contains the X, Y, Z coordinates of every atom that's in the molecule, and that's actually shown here. So the first atom is the nitrogen of lysine, and it's amino acid 1. And here it is. Here's the X coordinate at minus 9.890. The Y coordinate is 2.995. And the Z coordinate is minus 17.920. These last two terms have to do with statistics and fitting that atom into the corresponding electron density resulting from diffraction. So we won't go into that. But you can see here literally what Pymol is reading, or any software that renders structure. What is it reading when it reads a PDB file are these X, Y, Z coordinates, and it plots them as if you're plotting points on a three-dimensional X, Y, Z coordinate graph. You can go all the way down. Every atom is mapped to an X, Y, and Z coordinate. The 991st atom is a nitrogen from amino acid 128. It's the side chain nitrogen from arginine, and here it's X, Y, and Z coordinates. We also have water molecules. Water represents a heteroatom. It's not part of the protein chain, but water also comes into the crystal structure. And for all the water molecules, we have X, Y, and Z coordinates. You get information about the organism and any other things, whether any other compounds, any compounds that were co-crystallized with the protein structure, how it was crystallized, with regards to methods, symmetry, and resolution. Resolution is also a very important term in X-ray crystallography. So here's an anatomy of a PDB file, and I thought for those more interested students, they could take a look and see what this actually looks like.